we talked about this. From this point onwards, we are going to always write the governing equation in this divergence form, where instead of just writing your Laplacian operator, we are going to write this as the divergence of a gradient. Okay, and we can arbitrarily introduce the scalar quantity gamma in here, so that we have a more generalized form of the Poisson equation. Why? Because that's how the physical equations look like. For example, you'll have divergence of a heat flux, and the heat flux will have K grad T. Okay, thermal conductivity times temperature gradient. So that's the reason we are writing it that way, to make it more general. Okay, so I talked a little bit about this last time, but I just want to clarify all the math that you see here and all the symbols for those of you who have been far away from calculus for a while. Okay, so here's the so-called gradient operator, or this symbol is also sometimes known as nabla. Okay, that's the Greek name for this symbol. So that's what this stands for. It's really a vector operator which says I'm going to operate this on something, and you will see in a moment what that means. Now suppose I operate this on a scalar quantity phi, okay, like we have here, then this is called the gradient of the scalar. Okay, so what happens here is you simply insert the phi here, so you're operating this on the gradient. Okay, and basically this becomes d phi dx times I plus d phi dy times j plus d phi dz times k. Notice that gradient of a scalar is now a vector. It has three components. Okay, so if I take temperature and take its gradient, then that becomes a vector, and when I multiply it by the thermal conductivity, that gives me the heat flux in the three different directions: qx, qy, qz. Okay, so that's what this is showing. If I multiply this by a scalar, I get my flux. Now, of course, in the last class I mentioned that usually you have a minus sign in front, and that's just to obey the second law of thermodynamics. But from a mathematical standpoint, that's not important. Okay, bottom line is you have a scalar multiplied by a gradient. Okay, and then you get these three components: jx, jy, jz. And this is true for any quantity. You can think about heat flux, mass flux, current density vectors. Okay, all of them will have this kind of a form. So in undergraduate heat transfer, for example, you've been studying writing boundary conditions as k dt dx is equal to h times t minus t infinity. Okay, that's where that comes from. It's the flux that you're balancing. All right, so it's a vector quantity. All right, so getting back to our equation, we just looked at what this guy looks in Cartesian coordinates. Okay, so that's what we just derived. Now we have divergence of this quantity. So what we are doing is we take this guy, plug it in here, and now the divergence means this is a dot product. Okay, obviously here we have a vector. Okay, this is a vector quantity, as you can see. Here we have another vector. That operator, it's a vector operator. We just can't multiply the two. Okay, we either need to do a cross product or a dot product. Okay, if you do a cross product, that's known as the curl of the vector. If you do a dot product, that's known as the divergence of the vector. Okay, so here we are doing a divergence. That's because that's what's in our governing equation, and essentially this is nothing but a dot product between two vectors. So you can see I'm going to have I dot I, which is going to give me a 1, and that's why I get ddx of this first quantity. Then I'm going to get j dot I, which is going to give me ddy of gamma d phi dx, and that term is absent there because j dot I is 0. Okay, and so on. So all the terms cancel out except the I dot I, j dot j, and k dot k, which give us each one of them give us a 1. Okay, and we are left with these three terms. Okay, so this is known as the divergence form of the governing equation, where you have ddx of some flux. Okay, so that's our final governing equation in Cartesian coordinates. So when I write this equation, that's what it means when you expand it out. Okay. Of course, if you set gamma equal to 1, you get d square phi dx square plus d square phi dy square plus d square phi dz square equal to s phi, which is the Poisson equation that we've been working with until now. Any questions? All right. So, in the finite volume method, right away, big difference with finite difference. Okay. In finite difference, what we would have done is we would have taken this equation straight away, applied Taylor series expansions, okay, and approximated those derivatives. That's what we did all along. Okay. Our central difference formula gave us approximations to those derivatives. Okay, and that is why when we do finite difference solution, it is known as the strong form solution. Okay, the word strong form or the phrase strong form comes from the fact that we are solving the governing differential equation directly without any kind of modification. Yes, we are making some approximations to the derivatives, but we are not, differentiating the equation one more time or integrating it one more time or manipulating it in some way before solving it. Okay, but that's what we are going to do in the finite volume method, and the finite element method also does the same thing. Okay, the finite element method, at least the Galerkin formulation, multiplies this equation by a test function and then integrates it over the volume before it substitutes in the basis functions. Okay. So finite volume, we pretty much employ the same kind of idea as a finite element method. In finite element method, on both sides of the equation, we have a test function that multiplies this because it's a variational formulation. Here we don't have that. We are simply integrating both sides of the equation over a arbitrary volume V naught. Okay, this is your control volume that you're looking at. Okay, so now, of course, this is what we are representing by J. So ultimately, it comes down to divergence of a flux vector J. Okay. And using the Gauss-divergence theorem, we convert it to a surface integral. So the Gauss-divergence theorem is exactly what I've written here. It says when I have divergence of a vector and I do a volume integral of that, that becomes a surface integral of the vector, the normal component of the vector multiplied by the area. I kind of showed you this in the last class where I showed you this, heat flux example where we took J dot n, summed it over the entire boundary, and then we went backwards and converted it to a volume integral to derive our differential equation. Okay, here we are going the other way. Okay. So this guy is, the Gauss-divergence theorem is sort of our bread and butter theorem that we always use in the finite volume method to convert volume integrals to surface integrals. Okay. So n is the outward pointing surface normal. So basically what we are looking at is if I have a volume here, I have a differential area here, dA. Okay. N is outward pointing surface normal, unit surface normal. Okay. And J, as I said, could be an arbitrary flux like that. So J dot n gives me the normal component, and then I'm multiplying it with the area, summing it over the entire area. Okay. So it essentially gives us physically out minus in out of that control volume. Okay. It's out minus in and not in minus out because our surface normal is pointing outwards. If the surface normal was pointing inwards, it would be in minus out. All right. Okay. Now, in the finite volume method, all information is stored at the cell centers. Okay. So, we have this Cartesian mesh. When we look at finite difference, the nodes are actually at the intersection of the lines, right? In the finite volume method, we are saying no, the nodes are placed at the centers of those little squares that we generate out of that wireframe structure. Okay, I'll show you a picture in a moment. So one of the critical assumptions is that the volume average of any quantity is identical to the value of the quantity evaluated at the cell center. Okay, long sentence. I'll just explain in a little bit what that means. So basically, we're saying this, that Suppose I do an integration of a function 0 to 1 f of x dx. Okay? So this is what I'm trying to integrate, let's say. Okay? Now, in the finite volume method, what it says is that this will be approximately equal to f at x equal to half times delta x. Delta x would be basically 1 minus 0. That's the approximation it's making. Okay? So now you might say, well, when is this true and when is this not true? Okay? If this function is linear, obviously this is always true, because the average of a linear function is always in the middle. Okay? There are many other functions for which also this will be true. Okay? Depends on the function. In general, as you shrink the gap between the top and the bottom, this delta x I'm going to call it, okay? As you shrink delta x, this approximation will become more and more accurate. Why? Because every nonlinear function can be approximated by piecewise linear functions in the limit that you take the interval to be very small. That's basically calculus itself. Okay? That's what calculus tells us. So this approximation becomes exact in the limit that you refine your mesh considerably. Okay? In fact, if you do an analysis of this, you can show that this is approximately, there's a truncation error associated with this, which is also of order delta x squared approximately. Okay? So in other words, by making this approximation, we are not introducing any additional error. We are making the same kind of errors that we make in the discretization process that we'll talk about in a moment. Okay? But this is one of the fundamental assumptions in the finite volume method. In other words, every quantity that you have, you're taking basically, you're storing it at the cell center, and the cell center value essentially you're assuming represents the average. Okay? Whether it's in a volume or whether it's at a surface area, same thing. Okay? If I have a surface and I'm saying, okay, I'm storing the flux at the center of that surface, okay, then basically I'm saying the center value of the flux represents the average flux over that face. Okay? All right, so that's what this statement refers to. We're saying the volume average of any quantity is identical to the value of the quantity evaluated at the cell center. All right? Under this assumption, the volume average of S phi, which is on our right hand side right here, this guy, okay, it may be assumed to be its value evaluated at the cell center, and so therefore we can write that, okay, which is basically the general form of that fx dx equation that I wrote in the previous page. All right. So this indicates that this is S phi evaluated at the cell center times the volume of that cell. Okay? Because the definition of a volume average is that's the definition of volume average of any quantity. Okay? So that's what we are essentially using here. So our final result then becomes that, okay, the surface integral of the flux, the normal component of the flux, is equal to the source term. Okay? So this equation that we just derived, if you go back and look at the steps we took to derive it, there is no approximation whatsoever in terms of what control volume shape or what its size, or, you know, it's valid for an arbitrary control volume. There's no restriction there. Okay? So when we start, for example, with unstructured finite volume formulations, this is where we'll always start. Okay? It does not rely on the fact that your mesh has to be orthogonal Cartesian. Now we are going to make a further approximation. So now we are relying on the fact that we are saying in a computational framework, the control volumes are bounded by a finite number of planar faces or linear faces in 2D. In other words, we don't usually have from our mesh generator control volumes which look like that. Okay, no mesh generator will generate that kind of a control volume. It will always generate a control volume which may look like that. Polygons in 2D or polyhedrons in 3D. Okay, so what we're saying is they're bound by a discrete number of planar or linear faces. Planar in 3D, linear in 2D. Okay, so therefore what we can say is we can simplify this guy, this surface integral further. What we can say is, and I'm going to there's a step missing in going from the top equation here to the bottom equation, so I'm going to sort of elaborate on that a little bit here. Okay, so here is what happens. We start with this. Okay, now this surface that we are talking about, suppose I have a control volume which looks like this triangle. Okay, this surface can be broken up into three faces, three segments, right? So this surface I can write as integral, okay, so this is S, by the way, SI, and then gamma grad phi dot n dA. So what I've done is I've broken up this full integral into three segments, each one going along that edge. Okay, so I is going from 1 to 3, and then now I'm integrating over SI, each of the segments. Okay, everybody understand that? So simply broken up the entire surface area into three segments for this example that we are looking at. All right, now in each of those segments the surface normal is constant. So the surface normal here is constant, here is constant, here is constant. If these edges were curved edges, the surface normal wouldn't be constant. It would be changing. Okay, but here they are straight edges or planar faces, so therefore they have a unique surface normal. Okay, that surface normal is not changing. So therefore this guy is a constant. That's one thing to understand. Second thing is, now we are going to again use our average representation and say that, okay, this is our J. Okay, we are going to say JF is 1 over area of the face integral over the area of the face, okay, of gamma grad phi dA. So essentially what we are doing is we are replacing this integral that we have. The n can go outside the integral, and the rest of it, gamma grad phi dA, okay, integrated over this SI, can be written as this guy, where J now represents the average flux rather than the local flux at the face. So we have what we have done in going from here to here is that we have again used the definition of the average, and again we are saying that the value evaluated at the face, by face we mean now face center, is the same as the average value of the flux. Okay, that's an approximation, just like we did for volume. Okay, everybody understand that? Yeah.
So that assumes that the surface normal is constant.
Yes, that assumes the surface normal is constant. Otherwise, this is not really an average of the flux. It's an average. It would be the average of the normal flux. Okay. So the interpretation changes slightly. Any other questions? All right. So that's our final equation then for a control volume bounded by planar faces or straight edges. Okay. Again, the shape of the control volume can be arbitrary. Okay. All right, so that's our equation. Now, as I said, there is no assumption regarding the control volume shape or size. to derive this equation. To proceed further, what we have now to do is, again, we still have the gradient here. We can't work with the gradient. Obviously, our computer doesn't understand gradients. So we have to convert that to an algebraic form, okay, just like we did in the finite difference method. So in the finite difference method, we had second derivatives. Now we have first derivatives in this equation, which we need to approximate, okay? Now, as a starting point, to simplify this equation further, we are going to take a Cartesian mesh, okay? And here is a stencil that you are familiar with. So your finite difference nodes were located here. So in other words, the vertices of the control volume were your finite difference nodes, okay? But now we have these cell centers that I've shown in blue circles, okay? And again, we use these directional notations. I explained this in the last class already. If you write in terms of those global indices that you've been using for setting up your matrices and so forth, same idea here. This is k plus 1, k minus 1, k plus n, k minus n. Okay, same idea. It's almost as if the whole thing has just shifted by half a cell, because then we were applying those to the nodes. Okay. So the green arrows represent your surface normals. Okay, so cell centers denoted by capital letters, cell faces denoted by small letters. Surface normals are denoted in green, and by definition they're pointing outwards from the control volume to be compliant with the divergence theorem that we used to derive the equation. Okay. So for this particular control volume that I showed in the previous page with 4 edges, this summation basically becomes a sum of 4 terms. Okay, east, west, north, south. So instead of F, I'm using the small letters east, west, north, south. Okay, summation over 4 faces. So here's our stencil. Let's look at each of the individual terms in that equation. We start with this guy on the right hand side, volume. Volume is nothing but delta x times delta y for that particular control volume. Okay. Area of the eastern face, which we have in that term, all these areas. Okay, for this 2D Cartesian stencil, they are nothing but AE, A west is delta y, and A naught, A south is delta x. Okay. Going further down, N east, that's showing up here, is your unit vector in the x direction. N west, similarly, is the negative unit vector in the x direction. Okay, because it's pointing the other way. And similarly, A naught is j, and A south is minus j. Okay, so those are your 4 surface normals. So now we take all this information and plug it into that equation. Okay, grad phi is that. So grad phi shows up in each of these terms. So grad phi at the eastern face would be simply d phi dx at the eastern face times I plus d phi dy at the eastern face times j, and so on. Okay. So this term that shows up in the first term in the previous slide, okay, is simply this at the eastern face dotted with I. That gives me d phi dx at the eastern face. Okay, so that goes in. So, and then similarly we do the same math for the other 4 terms. We get negative d phi dy at the western face, d phi dx at the western face, d phi dy at the northern face, and negative d phi dy at the southern face. Okay, we plug all that into our governing equation. This is what we end up getting. Okay, everybody follow that? All right. Next task is to express all these quantities at the faces. So these guys, these derivatives at the faces, in terms of the cell center values of phi at the east, west, north, and south locations, okay, or cell center values. Okay, now we've introduced this new scalar gamma. How do we evaluate that? Well, obviously, as I said, this information is stored at cell centers only, not at faces. So we have to find face values, and the way to do that is to do interpolation. Okay, so you do a simple linear interpolation in most cases. Now there are cases where linear interpolation wouldn't work, but we'll talk about that later if we get a chance. That happens when you have material property discontinuities. Like for example, if you have a thermal conductivity of 1 in one region and 100 in the other region, that's a discontinuity in gamma. Okay, and these kinds of expressions wouldn't work for that case. Okay, because these expressions, interpolation, remember, is based on Taylor series expansions essentially, and that doesn't work for discontinuous functions. Okay, so but in any case, in general, this is the kind of thing you would do. Now, if it's a non-uniform mesh, then you would do distance-weighted interpolation. Okay, here I'm just doing a straight average because it's a uniform mesh. Okay, now let's talk about the derivatives. This is the most important thing. So what we are doing here is we want to derive this guy, right? So that's our goal. So therefore that should be our pivot point, because this is what we are trying to derive, d phi dx at the eastern phase. Okay, so we do one forward expansion. This is half a delta x away. Okay, because what we have here is, here's your node naught, node east. Okay, and this is your eastern face. So we are expanding this about that, which is delta x over 2 away, and then same thing here, this about that, which is negative delta x over 2 away. So the negative expansions obviously have negative signs in the odd terms as before. Okay, now we want to derive an expression for the first derivative. So what do? We subtract the two equations, because if we add them, that will cancel out. Okay, so we subtract the two equations. That gives us phi east minus phi naught is delta x d phi dx plus the cubic term. Notice that this guy and this guy will cancel out if you subtract. Okay, so we are left with the next term. And if you rearrange this, this is what you get for d phi dx at the eastern phase. Okay, it's the exact same idea as we used for finite differences: one forward Taylor series expansion, one backward Taylor series expansion, and therefore this method, this scheme that we just derived, is known as a central difference scheme. Okay, we could have, for example, done two forward Taylor series expansions or two backward Taylor series expansions to derive a first derivative. That would have worked too. We just didn't choose to do it. Okay, so that gives us the central difference scheme. Notice that the order of the approximation is second order, just like your finite difference. Okay, except that this is an approximation for the first derivative, not the second derivative. All right. So that's what I'm saying here. Proportional to delta x square, as in the case of finite difference, second order accurate. Similar expressions you can derive for all the other first derivatives in that equation, and once you plug it in, this is what you get. Okay, so this is your gamma east, this is your d phi dx east, gamma west, d phi dx west, and so on. Okay, now here is one. Okay, so this is the 5-band form again. So we are back to square one in the sense that everything that we did for finite difference methods in terms of solving the equations, those same things we can use again. We have that 5-band form. Remember that E, H, B, whatever you use for the Stone's method, same idea here. Okay, can fit directly into that framework. All right. If you assemble all the terms nicely, then this is what you get. And here is what happens when you assume that gamma is equal to 1 and delta x is equal to delta y. Well, delta x equal to delta y you don't have to assume, but gamma equal to 1. When you do that, this is what you get. Okay. Now what is that? That is the finite difference equation that we had derived maybe 15 lectures ago for the Poisson equation. Okay, so, and this is the reason why many textbooks claim finite difference, finite volume, same thing. Okay, they look at these equations and they say, oh, it's the same equation, so it must be the same method. The answer is no, it's not the same method. It is the same method for equal mesh spacing with gamma equal to 1. First of all, those assumptions, and then the same equations show up only for interior cells. When we go to boundaries, it will be completely different. Okay? But that's just something to understand, that the structure of the equations and the form of the equation is identical in the two methods. Okay? The order of the approximations also the same. So one point to note, though, is that the error expressions are slightly different, although both are second order accurate. For example, just going back to here, okay, if you recall, the error expression in finite difference was negative 1 over 12 delta x square. That. Here it's different. Okay, this one has third derivative, that one had fourth derivative, which makes sense because we have integrated the equation once already. Okay, so the order of the derivative went up by 1. Okay, but the bottom line is this guy, which tells us that as we refine the mesh, the behavior of the errors, the scaling behavior of the errors will be identical. Okay. All right. So we do not have, talking about boundaries, so I'm moving on to talk about boundaries. We do not have nodes at the boundaries. We only have cell centers. So therefore, this equation that I derived here, not that one, but let's go back a few slides. This guy, this is still valid for all cell centers, including cell centers next to boundaries. This is quite different from finite difference approximations, where you had to do, special considerations for boundary nodes. Here, the finite volume equation, the basic finite volume equation, is applicable to all nodes or all cell centers. Okay, the only difference will be in how you derive the discrete approximations for these derivatives. That will be the only difference. Okay, so let's talk about that. Okay, boundary conditions. So the derivation of the finite volume equation. So before I talk about boundary conditions, here is I have a couple of slides here to show you a different viewpoint. Okay, by that I mean here up on top we applied the divergence theorem to get this equation. Okay, and then we reduced it using our particular orthogonal stencil, and then figuring out all the terms and then plugging it in. Now, could we have done it differently? Okay, could we not have used the divergence theorem at all? What if the equation was not in divergence form at all? In other words, if we were solving something like what you have in structural mechanics, for example, something like that, okay, which is not in divergence form, how would you then, apply the finite volume procedure? So that's what I'm about to talk about, that could we have derived these equations in a different way? And the answer is yes, you can. You don't have to use the divergence theorem. Okay. And this is how you do it. So you start with your governing equation again. Okay. And now, again, like we said in the finite volume method, we always integrate over the control volume first. So that's what we are doing. We are integrating over the volume, both sides of the equation. Okay. At this point in the previous derivation, we applied the divergence theorem and converted the left-hand side to a surface integral. We are not going to do that anymore here. Okay. Your dv here for a Cartesian stencil is dx dy. All right. So the integral over volume simply becomes a double integral from south to north, west to east. So basically we are looking at this stencil here. Okay, we are going from south to north and from west to east. Okay, on both sides. So that's our equation. We are going to integrate. So first what I do is, this one is a perfect differential, so this can be written as gamma d phi dx east minus gamma d phi dx west. Okay, and we have the north to south to north still there, dy, and then here I reverse the integration order. So what I've done is I've done south to north first, and therefore this is a perfect differential in y. I get gamma d phi dy north minus gamma d phi dy south, and then the west to east stays intact. Okay, this is where I again use the definition of the average. Okay, and I'm going to write this as that, where this essentially represents the value evaluated at the center of the face, but the interpretation is that that's approximately equal to the average of that quantity over that face. Okay, so that's what the next step is doing. Okay, I say here fluxes are constant, but this is not quite correct. What we are assuming here is, again, the mean value theorem, essentially. All right, so we get that, and now we are back to our original equation of basically j east minus j west, which are the fluxes, times delta y plus j naught minus j south delta x is equal to S naught times delta x delta y. Okay, so this is with direct integration without, applying the divergence theorem. The advantage of applying the divergence theorem is that it lets you then use that for any arbitrary shape. Here, of course, we could do that, for a perfectly Cartesian stencil. If we had a control volume even like that, which is not aligned to the grid lines, you can't even define the limits of your x and y anymore. Okay, so you can't perform that integration easily. Okay, so let's move on to boundary conditions. So the fundamental difference with finite difference is that we do not have a node or cell center at the boundary. All cells are interior. And the Dirichlet boundary condition is actually applied to a cell face indirectly. Okay, so here is the idea. Here is a boundary. This quantity here, phi at the western face, is known. Okay, we are trying to derive a finite volume equation for that control volume next to the boundary. Okay, as you can see, the cell center is not on the boundary. It's an interior cell center essentially. Okay, so if I integrate my governing equation, I still have this same equation. Nothing has changed, as I mentioned. The only difference is that the way we approximate this term, the western face flux, is going to be different, because I can't use, this minus that divided by 2 delta x anymore, or sorry, divided by delta x anymore, because I don't have a cell center to the west of that boundary. Okay, see, for example, for this guy, I'm going to use this minus that divided by delta x. Okay, I can't do the same for the western face. Okay, so that's the only difference. All other terms I can still do. For example, the d phi dy at the northern face, I can do phi at that point minus phi at that point divided by delta y. Okay, that doesn't change. Same thing for this guy. This minus that divided by delta y. So the east, north, south stays unchanged. The only change will be in the western flux. How do we do that? We do now 2 forward Taylor series expansions, because we cannot do central differencing anymore. One of them is phi k. Let me just wipe this so you can see clearly. So phi k about phi west, right there. Okay, so that point about that point. That's the forward half. We already did that for interior nodes also, but now we are also going to do k plus 1 about phi west. This guy about that. And that has spacing 3 delta x over 2. Okay, so 2 forward expansions. We want to derive an expression for this guy. Okay, so to be able to derive an expression for this guy, which is high order accuracy or second order accurate, I must cancel the second derivatives. If I don't cancel the second derivatives, I'm going to get only first order accuracy. So that's why I'm multiplying the first equation by 9, so that this term here and that term there cancels out. Okay? Then we subtract. So we, on the left hand side we have that, right hand side we get 9 phi west or 8 phi west, and then we have the remainder. We rearrange. So d phi dx at the western face then becomes this expression with again a second order error. Okay. The reason we use two Taylor series expansions is because we want a second order error. If we wanted just a first order approximation, we could have used just one Taylor series expansion. Okay, but we don't want to contaminate the solution and the interior nodes or interior cells with a first order approximation at the boundary. So it's a good idea to stay consistent with the order of your scheme. Okay, so that's what we have derived here. So now we take that and we plug it into this term here. Okay, and we get that. Every other term stays the same as we had for interior nodes or interior cells. No change. Okay. Now we apply our boundary condition. Phi at the western face is equal to phi left. Okay, that goes in here. Once I put it in here, that particular term, that times the gamma becomes a known quantity. So I've transposed it to the right hand side of the equation. It goes into the source vector. Okay, and this is now your 5-band form for cells that are adjacent to the left face. Okay, it's quite a bit more tedious than Dirichlet boundary conditions for finite difference, where all you had to do was put a 1 in your diagonal and phi left on the right hand side and you're done. Now you have to actually derive a nodal equation for those cells. Okay, when we apply Dirichlet boundary conditions. But there is a good side to the story and the good side of that story is when we get to Neumann boundary conditions. The roles get reversed. If you apply Neumann boundary conditions in finite difference, then you have to derive the nodal equations using Taylor series expansions, okay, which we haven't done too much in our class, except that you are now doing it for the time-dependent problem. Remember, on the two edges you have, or at least on the left end, you have Neumann boundary condition, d phi dx equal to 0 in the problem that you're solving for, and you had to derive a nodal equation there. Okay. Here, it's much easier for the finite volume method. All you do is, this is your equation, your flux is simply some known value, J. Okay, I'm calling it F here. So this is known directly. Okay, d phi dx is equal to F. That's your boundary condition, Neumann boundary condition. Okay, so you simply plug that in there and then transpose that term over to the right hand side and you're done. Okay. So it's sort of a role reversal. In finite difference, Dirichlet boundary conditions are easy to implement. Neumann boundary conditions are difficult. Here, it's the other way around. Neumann boundary conditions are very straightforward. Dirichlet boundary conditions are a little bit tricky. Any questions on that? On the derivation of the boundary conditions? So the moral of the story here, or the takeaway, is that you always start from a flux equation like that. This flux equation is essentially, make it a habit of starting from there. Okay, don't do it any other way. I had a summary here. This is the equation you should start with always. Later on, for those of you who are going to go ahead and do, let's say, classes in computational fluid dynamics and so forth, this is what you will start with. And then the J may have, advection, diffusion, all kinds of mechanisms in it, but that's ultimately what you start with, the flux balance equation. Okay. Here we are just looking at a diffusion problem, and so therefore our starting point becomes that. But again, that's what you start with, and then you look at each of the terms and say, okay, which ones do I need to approximate? And then you go ahead and do your Taylor series expansions and approximate that. Okay. All right, let's talk about the final boundary condition type, the mixed kind, or the Robin boundary condition. Okay, which is also known as the boundary condition of the third kind. Here we have a combination of the derivative and the value of phi equal to a constant. So a d phi dx plus b phi equal to c. Okay, this is kind of like a Newton Cooling boundary condition for heat transfer. I already mentioned this. So again, this is what we want to approximate. So what do? We again do the two Taylor series expansions, just like we did for Dirichlet boundary condition. So this is a repetition. All right. And we plug in the boundary conditions. So what we do is we take this equation, okay, and rewrite it in this form. So we express phi west in terms of the gradient on the west at the western face using the boundary condition, and then we plug that in here into both expressions. Okay. So once you plug that in, this is what you get. You rearrange, okay, or well, even before rearranging, you multiply this by 9 and then subtract the second equation. That gives you this. Okay. And then you rearrange, and your d phi dx at the western face comes out to be that. Notice that it has nodal value next to the boundary and then one even further away, and then all these constants that were there in the boundary condition. Okay. Now here it's a little bit tricky. You have a 3 delta x cubed divided by some quantity which is of order or have the units of delta x. So roughly it's delta x square, although it's hard to directly say that it's delta x square, but you can see it's a cube divided by delta x itself. All right. So that's your expression, and now you plug that into the flux expression right there, and then rearrange, and that becomes your 5-band form. Okay. Any questions on that? Now for corner cells, there will be 2 boundary faces, and the same procedure you have to apply to both boundary faces. So in other words, if I have a corner like that, okay, and I'll just make up an example here. Suppose I say I know the value of phi here, I call it phi top, and the value of phi here, which is phi left. This is kind of like the Poisson equation that you've been solving all along. Okay, so I have that. So I want to derive now an equation for this control volume. So what do? I go back to my equation, which says gamma east d phi dx at the east minus gamma west d phi dx at the west times delta y. Okay, and then I have plus gamma north d phi dy north minus gamma south d phi dy south times delta x. This is what I had. So now you can see what I have to modify is this guy, because this is a western face, the control volume, and also what I have to modify is this guy, which is the northern face of the control volume. Okay, so for the western face of the control volume, the treatment is exactly what I had for Dirichlet boundary conditions up on top, right here. Okay, I'm going to plug in that expression. Okay, nothing has changed. So that will go in for the western face. Okay, right here. And then for the northern face, I'm going to do Taylor series expansions of this about that face and then this about that face, and I'm going to get almost an identical expression as I got for the western face, except instead of k and k plus 1, I'm going to have k and k minus n show up. Okay, and instead of phi west or phi left, I'm going to have phi north or phi top in that expression. And then that will go in here. And then after you've plugged those two expressions, you rearrange your equation and you have your nodal equation. Okay, does that make sense? So you don't necessarily have to derive it again and again. Once you've done left, right, top, bottom boundary conditions, it's pretty easy to see what will happen to the corners. Okay, it's just a superposition of the two. Okay, any questions?